Today we're going to do the 2016 Level 2 Mathematics paper, Calculus Methods in Solving Problems. So remember, this is just Level 2, so all of them are just going to be polynomials. There's not going to be any trig or logarithms or anything like that in this. So this is from the NCEA site, and I'm just going to use the calculus formulae that are given in the formula sheet and the Casio emulator. All right, first question. The function f is given by f of x equals 4x cubed minus 7x squared plus 2x minus the gradient. So you should be asking yourself, are we going to need to differentiate or integrate? You'll need to differentiate or integrate for all of these problems. The gradient is differentiation. So we're going to differentiate that and plug in 2 and see what we get. So if f of x is this, what we've already got. By the way, I always write the question down again so that you're not kind of jumping between things here. F dash of x just cuts down on the possibility of screw-ups. So 3 times 4 is 12x. This loses 1. 2 times negative 7 is negative 14x, and it becomes a 1 if you want to put it there, and the 2x becomes a 2, the minus 4 disappears. Then we plug in the 2 bit that we got up here, so we've got 12 times 2 squared minus 14 times 2 plus 2, so that's going to be 40. What happened there? Wow, that was 48 minus 28 plus 2 is going to be 22. So the gradient there is going to be 22 over 1. I write it in that form because it's, rise over run. So the second question says that we have the line y equals x plus 3.25 as tangent to the graph of the function f of x equals 3x squared minus 2x plus 4. And I've done them in GeoGebra here, and we can see, yep, sure enough, this does look like a tangency point there. Use calculus to show that the line is a tangent curve, is tangent to the curve, and that the point where this tangent touches the curve is here. Okay, so to find that this line here is a tangent to this one here, 2 conditions have to be met. It has to touch at that point and only that point. So like if we were to zoom in on this bit here, you couldn't have it kind of like, actually not like that, so that it sort of crosses into 2 places. It has to cross at once, and where they cross, they have to have the same gradient. So we're going to be finding the gradient, so we're going to be differentiating it. I'm not going to prove that that's where they cross, because it says it as a tangent, so we're going to take them at their word for that. So when we differentiate the first one, it's going to be really easy. So when we differentiate that, dy dx, there's a 1 in front of that x, so therefore the gradient is 1, which kind of makes sense that every 1 that we go across, we go up 1. And it's a straight line, so it's going to have the same gradient everywhere. Second one, maybe not quite so complex, but let's do it. I should say not quite so easy, but not much harder. So f of x is that, therefore f prime of x is going to be 3 times 2 is 6x. The exponent loses a power, so it's going to be to the power of 1. Don't really need that at all. And this is going to be x to the power of 0 minus 2. Then we would come along here and we would say, okay, so for each of these, we have the dy dx, and we're going to evaluate that when x equals, what was it, 0.5, and we get the following. So 1 times 0.5 is 0.5 plus 3.25 0.25, which is, no, I've done it wrong. So it's just at 1. What am I saying? Everywhere has the same. I've just gone down the screen saying how everywhere the gradient's the same. The gradient is going to be 1 everywhere, and f dash evaluated at 0.5 is going to be 6 times 0.5 minus 2. So that's going to be 6 times a half is 3, minus 2 is 1. So they have the same gradient. They cross at the same point. Therefore, that is tangent. Don't go off on a wild goose chase trying to prove that's the only point where they cross. You're just going to waste time. On with the next question. The function f of x is 2x cubed plus kx squared plus 5 has the minimum at the turning point where x equals 1. Find the coordinates of the maximum turning point. So this tells us we're going to need to do a few things. What's this going to look like? It means that when we take the differential of that and we put in x equals 1 here, so we put in a 1, it's going to equal 0. And also when we take the second derivative and we put in 1 there, it's going to be a number which is less than 0. Yes. Yep. Which means that the other turning point, when we differentiate it and we put in whatever that is going to be, it's going to be a maximum. No, I got that wrong. It's going to be greater than 0, isn't it? If it's a minimum point, yeah. So that's going to be less than 0, meaning that it's a maxima point. We have this problem here with k. So first thing we've got to do is we've got to differentiate it. So let's copy out the original equation here. And k, we're going to presume that that's a constant plus 5. Now when we differentiate that with respect to x, we're going to get 6x squared plus 2kx, and then the 5 is going to disappear. But we know that when we put in 1 in here, we're going to have that equal to 0. So therefore 6 times 1 squared plus 2k times 1 equals 0. So 6 times 1 squared is 6 plus 2k equals 0. And now we can solve this for k, can't we? So I'm going to take 6 away from both sides. So 2k is going to be equal to negative 6. Therefore, k must be equal to negative 6 divided by 2, which is negative 3. So our full equation, when we get rid of this k business, is going to be 2x cubed minus 3x squared plus 5. And now if we differentiate that one time, we're going to get 6x squared minus 6x, and then the 5 is going to disappear. And then to prove that it is a maximum or a minimum, we're going to differentiate it again. So it's going to be 12x minus 6. So what we're going to do is we're going to set this equal to 0 and then solve. We already know that one of these solutions is going to be 1, but let's do it anyway. So straight away we can see that we can, I guess we can divide both sides by 6. So x squared minus x is going to be equal to 0. We can factor out an x here. X minus 1 is 0, and this is the plus 1 that we've got. So therefore x equals 0 must be the location of the other turning point. And now we want to test that it is actually a maximum. So therefore f prime of x, where we evaluate x at 0, is going to be 6 times 0 squared minus 6 times 0, and that's going to be obviously 0. So that is going to be a turning point. It's actually going to be a saddle point at that point. And sure enough, when we come to graph that on GeoGebra, here we have our 0 point, which is obviously a maxima, and we have the minima point at 1, which is obviously a local minima. All right, third inning head. D, the equation of the function y equals f of x has the gradient function of the form f prime of x is 2x minus a, where a is a constant. The point 3, 4 is the turning point on the graph of the function. Find the equation of the function. Well, if this is the gradient function, we know that at the point where x equals 3, 2x minus a equals 0 by definition of being a turning point. Therefore, 2 times 3 minus a equals 0. So therefore 6 minus a, that's an a, not a 9, equals 0. So minus a equals minus 6. So therefore a equals positive 6. So therefore f prime of x is going to be 2x minus 6, because we know what a is now. Now to find the original equation, we're going to need to integrate that. So f dash of x is going to be the 2 stays there, the x stays there, we gain an indice, and we have to divide by that number, minus 6x, and we have to have that constant there at the end. So these are going to cancel. So this is going to be x squared minus 6x plus c. So we've got everything except for that c. How are we going to find the c? Well, we know what one of the points is. So you can read that point whenever x equals 3, y equals 4. So therefore 4 is going to be equal to 3 squared minus 6 times 3 plus c. And now we have one equation and one unknown. We can solve it. So 4 equals 9 minus 18 plus c. So therefore c must be equal to 4 plus 18 is 22 is 13. So therefore the original equation must be f of x is equal to x squared minus 6x plus 13. And we're done. Right, on to E. Find the local minimum value of the function y equals f cubed, brackets x minus 4. Justify your answer. So to find the minimum and maximum point, we need to differentiate that. So we need to find dy dx, and we need to justify the answer, which means we need to find the second derivative of that and see whether it is greater than or less than 0. So I don't like this brackets business, so I'm going to expand out the brackets. So we've got the original equation is this, x minus 4. So I've got x to the power of 4 minus 4x cubed, and it's just nicer to differentiate that. So when we differentiate that, dy dx is going to be 4x cubed minus 12x squared. And we're going to set that equal to 0 and then solve for x. Well, there's going to be a 4x squared. Is going to be a common term for both of those. So it's going to be x minus 3 is going to be the solutions. And then for that, we can deduce that 4x squared equals 0, which means x equals 0 is one of the solutions. And x minus 3 equals 0 is the solution. So x must be equal to 3. So the two solutions are going to be 0 and 3. So which one is the maxima, which one is the minima? Well, we need to take the second derivative of this. So if dy 12x, I'm just going to keep it in that polynomial form for now, and I'm going to differentiate that again. Take the second derivative, so that's going to be 12x squared minus 24x, and we're going to put in those two values for that and see which one is the maxima, which one is the minima. So 12 times 0 squared minus 24 times 0 is going to be 0. So that doesn't really tell us much. If we put in 3, 12 times 3 squared minus 24 times 3, 12 times 9, I'm not quite sure what that would be off the top of my head. 108 minus 24 times 3, 36. So 36 is definitely greater than 0, so therefore that's a minima. That tells us that the minima is when x equals 3, and then we have to put x equals 3 into the original equation to find out what the y coordinate for that is going to be. X cubed minus, so if y is x cubed, x minus 4 was the original equation, and we substitute in 3. So 3 cubed, 3 minus 4. So it's going to be 27 times negative 1, which is negative 27. So the local minima point is going to be at the point 3, comma, negative 27. On to question 2. The diagram below shows the function y equals f of x, and they want you to sketch what f prime of x is going to look like on the scales below. So from negative infinity to this point here, it's positively sloped. So directly above that, so it's going to be directly above that. And then from here to here, it's going to be negatively sloped. So from here to, what's that, about 1, it's going to be below. And then everywhere from there, it's going to be above. So it's going to kind of look like a parabola, like that. Right, moving along to B. So there is this little note here. The question has been corrected from that used in the examination, which kind of says that the one that was used in the examination had an error in it, which means that students may have been flailing around trying to find an answer that wasn't there. That's not good. Okay, but anyway, that doesn't matter to us because this is the corrected version. So this is the graph, so that's going to be a parabola opening upwards like that. It goes through the point 2, 3, and we need to find the tangent to the graph of the function at that point. So let's have a look at this one first, because if it's tangent, that means when x equals 2, y equals 3. So therefore 3 is going to be equal to a plus b. Does that help us? Does kind of, but no, it doesn't really, does it? Nope. Okay, well, let's differentiate it and find the gradient function then. So if y equals 2x squared minus 3x plus 1, so dy dx is going to be 4x minus 3. And then when we evaluate that when x equals 2, so 4 times 2 minus 3 is 8 minus 3 is 5. So that therefore the gradient at that point is 5, which tells us that the gradient of this is going to be 5 as well, which means that a is going to equal 5. So now this does actually come and help us. So 3 is going to be equal to, doing that again, 2 times 5 plus b. So 3 is going to be equal to 10 plus b. therefore b must be equal to -7. So therefore the line is of the gradient there is going to be 5x minus 7. And I'll leave it to you to prove that graphically if you want to. Moving ahead to C, the function f is given by f of x equals 2 minus 4x plus 2x squared plus ax cubed. Find the gradient of the graph of the function, the gradient of the graph of the function at the point where x equals 1 is 3. So therefore, if we differentiate that and evaluate that when x equals 1, so in other words, 1, we're going to get 3. And then we can use that to solve for a. Okay, so if f of x is given as this, plus ax cubed, I'm going to presume that a is a constant, f prime of x is going to be minus 4 plus 10x plus x squared. And we know that when x equals 1, this thing here should equal 3. So minus 4 plus 10 times 1 plus 3a 1 squared equals 3. We've got one equation and one unknown, so let's solve it. Minus 4 plus 10 plus 3a equals 3. So a equals minus 3. So therefore a must equal -1. All right, so now we get into the rates of change problems. A chemical is slowly leaking onto a floor. Chemical spreads out for the point where it lands in a shape that can be modeled by a circle of radius r centimeters. At time t seconds after the chemical leak is noticed, r is given by 0.1 t plus 2. Use calculus to find the rate of change of area of the circle with respect to time when its radius is 10 centimeters. So a lot of information there. Let's extract what we've got. So in other words, what's going to happen is here is the sort of the center of the circle. So at time t, oh, that's a terrible circle even by my standards. Let's get rid of that. Let's have another go. So at some time, that's a bit better. T, the radius there is going to be whatever it is. And then sometime later, the radius is going to be slightly bigger. So this radius is going to be increasing, which means the area is going to be increasing as time is increasing. Okay, so let's look at what we've got. We've got our little formula here. So we have area in terms of r, and that's pi r squared. We have the radius in terms of t. So radius as a function of t is given as 0.1 t plus 2. We're given an absolute number here where r equals 10. So at some stage r is going to equal 10. What is going to be the change of the area with respect to time? So in other words, we want to find the change of the area with respect to time. How are we going to do that? Well, we have a in terms of r and we have r in terms of t. So d to r is going to be 2 pi r. It's just this one differentiated with respect to r. And when we differentiate r with respect to time, we get 0.1. So it's going to be this one differentiated. All right, but we're looking for this. So can we get that out of this? Let's move up a bit. If we have dA with respect to r times dr with respect to t, these dRs are going to cancel out. And we're going to be left with dA over dt. Okay, that's what we want. So dA over dr is going to be 2 pi r times dr over dt, which is 0.1, which means it's going to be 0.2 pi r is going to be the rate of change of the area with respect to t. How does that help us? Well, we know we want to evaluate this when r equals 10. So that's going to be 0.2 pi times 10. So that's going to be 2 pi. So it's going to be growing at, 2 pi? 6.28 centimeters squared. So for e, we're told that a function is defined by y equals 3x cubed minus 2a squared x plus 5, where a is a positive number. Okay, find the range of values of x in terms of a for which this function is increasing. There's a lot of information there. So we know that a is a positive number, so a is greater than 0. And where it is decreasing would mean that dy dx is less than 0. And we want to find x in terms of a. All right. So let's find dy dx first. So if y is 3x cubed minus 4a, and presuming a is a constant, it says it's a positive number, so we'll take it as being a constant. So therefore, minus 4 times a constant squared is also going to be a constant, plus 5. So dy dx is going to be equal to 9x squared, which that's interesting, minus 4a squared. And we know that that has to be less than 0. That's interesting because this is the difference of two squares. We could, I guess we could at this stage set, we could go one of two ways. So this must be greater than 4a squared. So therefore, x squared must be greater than 4 over 9a squared. So therefore, x must be greater than square root of 4 over 9a squared. We could go that route, but I think this is going to help us because this is the difference of two squares. Remember, when we have a squared minus b squared, we can factorize that as a plus b, a minus b. So this is going to be x minus 3x plus 2a. And both those multiply must be greater than 0. So let's take them individually. So 3x minus 2a must be less than 0. And put that in terms of x. So 3x must be less than 2a. So x must be less than 2 over 3. Yep, that makes sense. 3x plus 2a must be less than 0. That was thunder just now. So I'm going to take 2a away from both sides. And x negative 2 over 3a. Yes. So if a is a positive number, that would mean that if a was positive 1, okay, so that means that a1 must be greater than 2 over minus 2 over 3. So minus 2 over 3a. Yeah, it's the only way that can be true. All right, question 3 already. The gradient function dy dx is 3x squared minus 5, and the original curve passes through the point 1, 0. Find the equation of the curve. So if we've got dy dx, and we want to get to just y, we need to integrate with respect to x. So we're going to integrate 3x squared minus 5 with respect to x. So the 3x stays, the 3 grows here. We have to divide by 3, minus 5x, and we have a c. So then we have, so I guess we can cancel those. So we've got x cubed minus 5x plus c. So we've got it up to c. How are we going to find c? Well, we're going to use this ordered pair, this initial condition that we've got, and that tells us that when x equals 1, y equals 0. So 0 is going to be equal to 1 cubed minus 5 times 1 plus c, and then we solve for c. So 0 is going to equal 1 minus 5 plus c. So therefore, c must equal 4. Yes, that makes sense. So our original equation is going to be of the form y equals x cubed minus 5x plus 4. That's our final answer for that one. Right, question B. So this is kind of reverse of the one that we had before. So here we've got the graph, but we have here a little bit hard to read there maybe. This is f prime of x. That's the fire station siren going, you can hear in the background there. So there is a bit of a storm coming over. So some poor person has probably had their roof blown off. And we need to find y of f of x. So what does that actually mean? It means we're going to have to integrate this. Here it is again. My dad used to be a firefighter, and whenever we heard the siren, he used to jump in his car and drive as fast as he could to the fire station. Not because he was necessarily wanted to put out the fire, although there was probably a lot of it. So he really loved driving the fire engine, I think. So first and got to drive, but anyway. So we need to integrate this. So what I'm going to do, I'm going to sort of find the equation of this, and we can see here that it sort of crosses there at 2 and negative 8, and then at negative 1, 2, 3, 4, and then at negative 8. So x, so it's going to be minus 4, and that's going to be positive 2. So x plus 4, x minus 2, which is going to give us x squared plus 2x. Plus 2x, yep. Plus 2x minus 8, and that kind of makes sense there because that's there. So this function is that. So if that's that function there. So if we integrate that, we're going to get x cubed over 3 plus 2x squared over 2. They're going to cancel. Minus 8x, and the plus c doesn't necessarily matter. So what does that tell us? How does it help us here? Well, everywhere from here across to there is going to have a positive slope. So going down here, let's choose some point there, and then everywhere from there it's going to be negatively sloped. So from here to here it's going to be negatively sloped, and then it's going to be positively sloped everywhere from there on. So it's going to be below this line. Actually, from here to here it's going to be below the line, and then it's going to cross that point there, and then the slope is going to be sort of flat there, and then it's going to be flat there as well at that point there. Let's actually put that in the calculator to see what that's going to look like. Okay. Yeah, these ones are always kind of tricky. So x, let's divide that by 3 over 3 plus x squared minus 8x. What does that look like? Okay, yeah, it's going to look kind of like that. Okay. So if we zoom out, it's not going to be a parabola, it's going to be a trinomial. Okay, so it's going to have that sort of N shape like that. So it's going to be flat here at this point here. So at some point there, it's going to be flat, and then it's going to be flat again at some point here, directly below that, and it's going to cross the x-axis at the minima there. Okay, so let's just kind of draw it then. So it's going to sort of go there like that, and then it's going to flatten off, and then it's going to be positively sloped. So the fact that this is above the x-axis means that when we differentiate it, it means that the gradient here is going to be positively sloped, and it's below the x-axis here, meaning that it's going to be negatively sloped, and then it's above the x-axis on this one, which means it's going to be positively sloped. So it's going to kind of look like that. Yeah, that's the rough shape. So we're up to the kinematics part of the exam. Meg is riding her motocross bike. Good for her. When she passes point P on the track, she has a speed V is 5 meters per second, and acceleration A is 0.6 meters per second. So they have speed and velocity interchangeable. The physics student should be scratching their desk at this point. If she were to continue to accelerate at this rate, what is her speed? Again, when she's been riding for 10 seconds. So the physics students have a bit of an advantage here because they do kinematics in physics, but we can get around that using calculus. So we know a couple of things from this. We know that we're looking for Vt evaluated when t equals 10 seconds. And we know that the acceleration as a function of time is just 0.6, regardless of how we go. So it's a constant acceleration. So every second she's going 0.6 meters per second faster than the second before. And we know also that V0, the initial velocity, is 5. And it's going to help us when we integrate this. We know also that Vt as a function of time is the integral of at as integrated with respect to t. And the constant term is going to be the initial velocity, which is 5. So let's integrate this. So we integrate this 0.6 to the power of 1. We're going to divide that by 1, but it's pretty silly to do that. Plus 5. So the velocity with respect to time is going to be 0.6 t plus 5. And when we evaluate that when t equals 10, 0.6 times 10 plus 5 is going to be 6 plus 5. So that's going to be 11 meters per second. And meters per second is velocity, so we're good. So now we're asked to find how far will she have traveled from P when she reaches a speed of 8 meters per second. So we're going to have to do a few things here. We're going to need to find how long has gone by the time she reaches this velocity, and then we're going to need to integrate the velocity function. So The displacement, I'm going to have S. And the reason I've got S is that D is already taken, obviously, when we got like dt and stuff like that. So the displacement S as a function of time is the integral of velocity as respect to time with respect to t. And the plus c is going to be the initial displacement, that is distance from when we started. So this is the start point here. The displacement here, S, as a function of time, is going to be this distance from here to here. The c here is going to be the initial displacement. Well, she's travelled no distance when time is 0. So c here is going to be plus 0. So Vt, we already worked it out. It was 0.6t plus 5. So we're going to integrate 0.6t plus 5 with respect to t. And we're going to get 0.6t squared divided by 2 plus 5t plus c plus 0. So we can ignore that, the constant term there. So we've got that. So that's going to be 0.3t squared plus 5t. So the displacement at any point in time is going to be equal to that. So how far will she have travelled from P when she reaches the speed of 8 meters per second? So we're going to take the velocity function and we're going to set that equal to 8 and solve t. So that's going to be 0.6t plus 5. Solving that for t, we're going to take 5 away from both sides. So 0.6t equals 3. So t is going to be equal to 3 divided by 0.6. I think I know what that is, but I'm not going to guess. So 3 divided by 0.6 is 5. So after 5 seconds. So then we could come along here and plug in 5 here and here, and we're going to find the distance that she's covered. So 0.3 times 5 squared plus 5 times 5. So it's going to be 0.3 times 25 plus 25, and I don't know what that is. 0.3 times 25 is that, plus 25, so 32.5 meters. 32.5 meters. So by the time she is at the velocity here of 8 meters per second, she's covered the distance of 32.5 meters. Last question. Meg's friend Leo was riding with her, but he begins to decelerate when they reach a speed of 8 meters per second, which is what we just worked out. So in other words, when t equals 5 and they've covered 32.5 meters. He decelerates at 0.2 meters per second. How far past point P when he reaches the speed? Where does this point P come from? Oh, passes a fixed point on the track. Okay, so P is here. So in other words, this is point P. So they go along here, they're accelerating, and then after that 5 seconds, he starts decelerating until he gets to a velocity of 6 meters per second. So t equals 5 there, and at some stage here, he's going to reach 6 meters per second, and we essentially want to know how much total distance he's covered in that time. Okay. So first off, we need to work out when he is going to be at that velocity. And for this, I'm going to ignore this bit here because we know that this is 32.5. And we're going to presume that it's in one direction. So it's not going there. It's not coming past back again. So we're going to take this T0 as being when he starts decelerating. So t equals 0 at time he starts decelerating, which is a negative acceleration. So, no, which is a deceleration, which is he's slowing down. So the acceleration at any point in time after there is going to be negative 0.2 because he's decelerating. I'm kind of thinking out loud here. Okay, and the initial velocity when t equals 0 in our model was 8, and the final velocity that we don't know is going to be 6, and we need to solve that for t. Okay, so vt is going to be negative 0.2 t, and then the initial velocity was 8, and we're going to set that equal to 6 and then solve for t. Okay, yep, I'm working it out in my head. So 0.2 t is going to be equal to negative 2, which means that t is going to be equal to negative 2 divided by negative 0.2, which is going to be 10 seconds. So in other words, t equals 10 seconds after he starts accelerating. He hits that point of 6 meters per second. Okay. So we've got t equals that. We've got the velocity function. Now we need to find the displacement function. We're evaluated where t equals 10. Again, we're ignoring this bit here for now. So time starts again here. And that's going to be the integral of the velocity function with respect to t. Okay. So the velocity function is negative 0.2 t. So negative 0.2 t squared over 2 plus 8 t, and the initial displacement when he passes p is going to be 0. Well, it's actually going to be this, isn't it? 32.5. Yes, because that's how far away we were. So we're kind of killing two birds with one stone there. And we're going to set t equal to 10. So negative 0.1 10 squared plus 8 times 10 plus 32.5 is going to be negative 10 plus 80 plus 32.5. So it's going to be 102.5 meters. That's going to be the distance that he's covered. Yes. 102.5. Okay. And that's the end of the exam. That was a pretty reasonable exam. I would have liked to know what their error was in the exam. I can't remember one being there, but if they've changed it after the fact, then yeah, there would have been some questions. Anyway, that was fun.
What about radiation?
Obviously down here it's nothing, but in the reactor building I'm being told 3.6 Röntgen per hour.
Well, that's not great, but it's not horrifying.
Not at all.